Stephen, for agreeing with this quick interview. It's a really pleasure for me to be here. And I would like to ask you a few questions about your trajectory over the years, and especially about your new perspective, the so-called new kind of science. So for those who are not familiar with new kind of science, could you just give like a brief overview what is the like key terms like rheology, new kind of science, computationally reducible and stuff like that, please?
Yeah. So, well, New Kind of Science is the title of a book that I published in 2002 that was sort of the result of work that I started doing in the early 1980s. And kind of the origin of that work was trying to understand how do complex things happen in the world. And I had been previously doing particle physics, mathematical physics, these kinds of things. My sort of plan A was use all kinds of fancy mathematical methods that I'd learnt in doing those kinds of things to figure out things about everyday kinds of phenomena in nature, like snowflake growth and fluid turbulence and those kinds of things. That didn't work. So then the question was, what else could you do? And the big idea that I had in the early 1980s was, how do you make models not using the sort of traditional methods of mathematics, but with some other kinds of rules? And so I started thinking about, well, what are the most general kinds of rules you can use to make models out of? And I realized you can think about those as little programs, just rules that say, I don't know, if you have a collection of black and white cells, at each step you make, the color of the next cell be based on the colors of cells on the step before. That's particular setup is a thing called the cellular automaton that I've studied at great length. So then early 1980s, I started looking at these very simple programs, very simple rules, see what they did. My first assumption was if the rules were sufficiently simple, the behavior that they would produce would be somehow correspondingly simple. This turned out not to be true. It was sort of my favorite, all-time favorite discovery, a thing called Rule 30, which is a particular cellular automaton rule where you just started off from one black cell, and it makes this very complicated pattern that has elements that seem completely random and so on. So this was kind of the big intuition breaking thing for me that happened in 1984. That was kind of it is not the case that simple programs, simple rules lead only to simple behavior. Simple programs can lead to very complicated behavior. To me, this seemed like sort of a secret that nature has been using for forever to kind of make complicated things in the world. And so I started studying this a whole bunch. And kind of the traditional view of how you make models of things had been you write down a mathematical equation, you try and figure out, you try and solve the equation, you try and get a formula for how the thing will behave. This is a different approach of saying you have these rules and you specify the rules, and that's you just run these rules and see what happens. So one of the big phenomena then is the thing I call computational irreducibility. When you have mathematical equations, you say, I'm going to solve these equations. I'm going to get a result that is a formula that tells me what's going to happen in the system, idealized Earth going around idealized sun or something, what's going to happen forever in the system. In the kind of approach of using programs, it's like you run the program step by step, you see what happens. The question is, can you computationally reduce that process? Can you jump ahead, say what's going to happen without following every step? Well, the claim is that no, you can't in general. In the computational universe, it's really common for things to be computationally irreducible. So the only way to know what will happen is essentially to run each step and see what it does. So this has all kinds of consequences, all kinds of implications, but that was sort of a key phenomenon for me. But then, the whole new kind of science effort was I spent the 1990s working on this big book that ends up being about as thick as it can be while maintaining binding technology that works. But in any case, the first question was these phenomena that I'd seen in cellular automata, how general were they? Did they apply to Turing machines and even to things in mathematics and so on? And what I discovered was, yes, they're very general. And I started looking at certain applications of those things, and I kind of made a little poke in applying those things to fundamental physics, but then stopped doing that and went back to my kind of day job of taking sort of the computational universe and making it useful to people by building our computational language, Wolfram language, to sort of take those aspects of computation which humans are interested in and make them as accessible as possible. So this notion of rulology is kind of it's a recent term that I've had for the study of simple programs and what they do, which I consider to be sort of a very fundamental thing. It's kind of more fundamental than mathematics in a sense. Mathematics, as normally practiced, starts from these very particular axioms and concepts and things about numbers and so on. Rulology is just you take a simple rule and you see what the consequences of it are. And the sort of the methodology of rulology, a lot of it is computer experiments. Some of it is sort of the philosophy of what can happen, but the end result is that you study these simple rules, see what they do, and there are many surprises. For me, I've been doing rulology for decades now, and every time I study one of these systems, it's kind of the thing I often say is the computational animals are always smarter than we are. They always manage to figure out some trick that we didn't think of about how to do some particular thing, how to not be subject to some limitation and so on. So I think this is rulology is a very, very nice area because it's an area where, in a sense, the frontier is very close to the beginning, and you can kind of, it's very accessible. You can, if you are a well-organized thinker about things, you can do rulology and you can contribute to it. And as you sort of add these, what do these particular simple rules do? It's sort of inevitable that if the rule is simple enough, it's going to be relevant for something. I mean, I've been really struck by the fact that there are 256 of the simplest cellular automata, and practically every single one of them has been applied to something. Yeah. And sometimes it's sort of weird for me because I've thought about an area, like one particularly dramatic one for me is road traffic flow, the formation of traffic jams. So I thought about that at one point, didn't figure anything much out. Then years later, it turns out that Rule 184 has become the standard minimal model for road traffic flow.
Wow.
And it's just one of these, if the model is simple enough, it's probably going to be applicable somewhere.
That's amazing. Based on what you're saying about computation irreducible, it's really close to me to what experimental physics is. Because sometimes you can make a theory, a prediction, what's going to happen, but the truth is only be revealed to you when you do the experiment. And in some sense, it's like this computational reducible, you say. What do you think about that?
Well, so that's true. I mean, computational irreducibility is a story of why you either have to do the experiment or do a detailed simulation of what's going to happen. We've been lucky in physics in a sense, in the sense that there is a fair amount that can be worked out in a computationally reducible way,
yeah,
where we can jump ahead. And like, for example, I don't know, something like fluid turbulence is probably not an example of that. Fluid turbulence is something where you have to kind of do the experiment, do the detailed simulation to know what will happen. Old Isaac Newton back in the day was sort of lucky that he studied, rigid body mechanics. He studied.
Reducible part.
Yes, it's a reducible part. He found a reducible part. And this is, there's a big challenge in a lot of fields. In physics, we've managed to slice off certain reducible features, and that's been the main sort of effort of physics. When in other fields, like biology, for example, it is not so clear that there are many reducible parts, and so there hasn't been much theory that's developed. And it's only been just do the experiments and see what's true. But yes, I think that the fact that sort of one has to just do the experiments is a story of computational reducibility. And I'm kind of reminded of an old obnoxious quote of Ernest Rutherford's that science consists of physics and stamp collecting, where stamp collecting was chemistry. And the point is that in chemistry, as far as Rutherford was concerned, there sort of wasn't regularity in chemistry. You couldn't theoretically work things out in chemistry. Well, it turns out in principle you can, but it's an area where there's plenty of computational irreducibility, and much of the time you're either doing a very detailed calculation or you're just doing the experiment and seeing what's true. And it's, I think, a tension in science of there are things where you can slice off this reducible part where there's a core of irreducibility where you kind of have to do experiments or simulations. And sometimes the reducible part that you can slice off will be a thing that's super useful, that allows you to do all kinds of engineering, build technology, and so on. Sometimes it will not be. Sometimes it'll be, well, that's an amusing effect, but it's not clear why we care about that effect. So it's kind of I think this is an important sort of tension in the development of theoretical science.
I see. Regarding other kinds of calculations that are very famous in the literature, like ab initio calculations or density functional theory calculations, do they fit, like, in your opinion, the reducible part of physics, or they are in the irreducible ones?
Good question. I mean, I think you know, there are some cases when you look at the answer and you say, gosh, this answer is very simple. We should have been able to figure this out in an easier way. That's a story of reducibility typically. When it's like, this is really complicated, you know, then it's probably a story of irreducibility. But how that, you know, how to think about that, I don't know. I mean, this question of sort of taking sort of the standard formalism of physics with continuous differential equations, things like this, and fitting that into a computational framework, it's not so easy.
Yeah.
I mean, we know, you know, that kind of, to really get there, we really have to start talking about sort of fundamental theories of physics and to what extent you can build that up computationally, rather than just saying, here is the sort of the existing differential equation. Now, what does it imply for kind of, you know, what does that imply computationally? I mean, I've long believed, for example, the three-body problem in celestial mechanics will turn out to be something that is computationally undecidable and so on, that can sort of do an arbitrary computation. But it's been very hard to figure that out, because it's very hard to make a bridge between sort of continuous mathematics and things that are computational. I mean, you know, in Wolfram language, for example, we obviously do lots of things with differential equations. Some of them we can do symbolically, where we're working things out in terms of you know, algebraic, you know, expressions and so on. Others we can only do numerically, and when we do them numerically, we're essentially breaking them down into some discrete thing underneath and just making the assumption. Sometimes you can prove it, but usually you can't. That when you make the sort of the numerical pieces small enough that they will approximate the continuum solution.
I see. Still regarding computationally reducible, there are some fancy theories that everyone's looking for, the so-called theory of everything. So is computation irreducible, like is going the opposite direction than a theory of everything, or they can merge at some point?
Well, what tends to happen is there are a lot of situations in which there's lots of computational irreducibility inside, but there's some slice of what goes on that is computationally reducible. I mean, in a sense, when we talk about laws of nature, we're talking about reducible things. We're talking about things where we see regularities, we can predict what's going to happen and so on. It's not obvious. One of the things that is sort of one of the biggest surprises in science, in a sense, is that science is possible.
Yeah.
I mean, it could be that the universe is just always doing unpredictable things, but what we have managed to do is to find these slices of the universe that we can sort of exist in, where there's enough regularity that we can have predictable things go on.
Can reproduce the results, you mean?
Yes, yes. I mean, well, or that we are describing kind of, well, take fluid mechanics, good example. At the microscopic level, there's a bunch of molecules bouncing around. Those molecular processes are a good example of computational irreducibility. There, you know, we can't work out in detail how these molecules are going to, the configuration they're going to end up in, except by basically running it and seeing what happens. But nevertheless, at a large scale, we have fluid mechanics, some aspects of which we can, you know, work out with simple mathematical formulas and so on. So that's a case where there's sort of a slice of this, there's computational irreducibility underneath. That the very fact that there's a reducibility leads to a certain kind of smoothness, it seems, in the fluid dynamics, which then allows us to have this kind of slice of predictable stuff at the level of fluid mechanics. Now, it's worth realizing that in that case, the fact that we believe in fluid mechanics, or we believe in the kind of laws of gas dynamics, is a consequence of the fact that we're observing fluids and gases and things at a scale that's very large compared to these molecules. We are effectively, you know, there's all this computational irreducibility underneath, all this complicated computation we'd have to make to figure out what in detail happens to every molecule. But all of that stuff turns out to be irrelevant when we just want to look at this kind of collective effect on a large scale. And that's, you know, the fact that the second law of thermodynamics, which says, you know, that things tend to get more random, the fact that we can believe in that law is a consequence of the fact that we are observers who only can sort of pay attention to sort of computationally bounded things. If we were noticing every detail of every molecular interaction, we wouldn't say, oh, it kind of just looks random and the entropy is increasing. We would say, well, there's this particular configuration of molecules which we can work out, and that's what's happening. So the fact that we are observers of the kind we are is the thing that leads us to believe in the second law of thermodynamics and to sort of have that view of the universe. So but I think in the end, all three of the big theories of 20th century physics, namely statistical mechanics and second law, general relativity, theory of space-time, and quantum mechanics, all three of them, I think, are a consequence of this interplay between underlying computational irreducibility and our computational limitations as observers. So, I think so in the end, this question of where are there slices of reducibility in this computationally irreducible world, those slices of reducibility are scientific laws. Where can we find them? That's a very interesting question. We can see there are a bunch of other domains, whether it's in foundations of mathematics, whether it's in neuroscience, whether it's in machine learning, whether it's in biology. They're all places where we can see there's computational irreducibility. The question is, can we find these kind of slices of reducibility? And when we find them, are they things that we care about?
Yeah, so we cannot draw a line to separate reducibility or irreducibility, right?
Well, within any computationally irreducible system, there are always slices of reducibility. That's an inevitable feature of computational irreducibility. So there's always more to discover. It's like in a computationally irreducible world, there are always little pieces of reducibility that you can discover. There are always inventions you can make. There are always discoveries you can make. It's sort of there's an infinite sequence of these things. And those are the pockets of reducibility are what lead to scientific laws of the kind that we know.
I see. And talking about a little bit more cellular automata, we notice that sometimes, for example, in quantum mechanics, we have like a continuum of energy, for example, or other kinds. Is it possible to reconcile this kind of continuum that nature sometimes shows with the kind of discrete behavior of cellular automata?
Yeah, I mean, this has been a question since antiquity: is the universe discrete or continuous, right? And turned out by the end of the 19th century, it's like, yes, molecules exist, matter is discrete. Yet much of matter seems very continuous to us.
Yeah.
I mean, water, the quintessential thing that flows, so to speak. So the discrete is kind of what can be underneath. The continuous is what observers on our scale of our type perceive about what's going on. And I think, one of the things that's foundational to these kind of theories of physics that I've worked on is that space is also not ultimately continuous, that space is also made of something discrete. And that's the fact that space is perceived by us as continuous as a consequence of the fact that we're observers of the kind and scale that we are.
I see. And changing a little bit about the subject, when we deal sometimes in physics, we calculate quantities that diverge, that goes to infinity. For example, in critical phenomena, when you go close to the critical point, you have the divergence of thermodynamic quantities. What do you think about these infinity quantities in physics?
Well, I mean, there are different kinds of infinities, and I think when you have this sort of discrete underlying model of physics, insofar as the universe is infinite in size or infinite in time, you're going to get infinite kinds of things going on. The question is, there are different kinds of infinities. So one that I've been thinking about recently has to do with thinking about quantum field theory and thinking about how that emerges from a discrete underlying model. And it's worth emphasizing that, cellular automata are a useful model of many kinds of phenomena in nature. They're not a good model of fundamental physics, because cellular automata kind of assume you have a grid of points in space and in time. And that's something that is not the way that space-time works. I mean, space-time is much floppier than that. And so, what I mostly studied is hypergraphs, generalizations of graphs, and sort of the rewriting of graphs. And that's kind of a way of having, in essentially, a floppier infrastructure, not this rigid grid, rather this arbitrary graph that sort of connects the atoms of space and that's getting rewritten in the course of time. So now the question is, well, what are examples of infinities there? And there are some interesting ones. So one that I've been looking at recently is what happens a big piece of what's going on is this notion of causal graphs. When you have a network that's getting rewritten, there are these rewriting events, and one rewriting event can affect another rewriting event. And so you can build up this graph of causality of this rewriting event is joined by a causal edge to this other one. You build up this causal graph of causal relationships. Well, the question is, are those causal relationships always sort of propagating forwards in time? Or can you have a loop where there's a causal effect of one thing, one event affects another event, that event affects back the previous event. That leads to something that is in a sense underneath, below time. Been sort of calling it
going back in time.
Yes, yes, but it's a loop in time. I've been sort of referring to, I'm not sure this name will survive, as subtime. This kind of what happens when you're kind of the actual causal edges, but the observer, like us, doesn't notice that there's this thing that's zipping around, in subtime. We only notice the sort of effects where things change because these little subtime loops are potentially everywhere. And so for us, it's just like that's the way that's kind of when we think about space-time, it is including all those little subtime loops. And that's those loops are, I think, related to infinities in quantum field theory. But you can use the same idea of normalization that is used in quantum field theory to say, there is a bare thing that's going on, but what we know about is what we perceive. And in the thing we perceive, that bare thing has been sort of canceled out by all these effects that are going on above it. So, that's a version of how that's one version of infinities in the kind of thing I've been looking at. I mean, okay, so in the kinds of things we've been looking at that are very computational, the question of what infinite processes look like is sort of an interesting thing. So usually if you're using Wolfram language or something, you type 2 + 2, it says 4, it's easy to compute that. Let's say you type x = x + 1. Okay, it will say, okay, you haven't given a value to x. What is x = x + 1? Well, it will loop infinitely because it will keep on adding to x, right? That thing is an infinite computational process. And there's a question of to what extent you can sort of classify the infinite computational processes. So probably there's a relationship between transfinite numbers and those infinite computational processes. You can kind of make in the case of x = x + 1, it's kind of it's just like counting. It's kind of like the ordinal numbers, and it's kind of the thing you get is kind of like a transfinite ordinal. You can, if you say x equals the list x, x, you get some kind of tree-like, infinite tree-like object. But so these are, this is a way that one sort of connects. This is computation and infinite computation. People don't usually think about infinite computation, but in our models, infinite computation and infinite physics are closely related. And there's sort of a question of how do you classify these infinite things? Maybe in terms of transfinite numbers, maybe there's a way in which there are only a limited number of infinities, like happens in quantum field theory, where you can apply this sort of idea of renormalization of just saying, we're just going to look at the effect, and we're not going to be thinking about kind of what the bare thing is before we started having things go on. So in the case of subtime, there is this thing that's sort of looping around in time, but what we get to pay attention to is this thing that's kind of at a higher level than that.
I see. So you're saying that there are infinities, and we still don't have somehow to classify and distinguish between them.
Well, I mean, I think that most of the time, so things which are infinite. So first of all, in the actuality of the universe, if the universe is made of atoms of space, there are a really large number of atoms of space, and our mathematical models can reasonably assume that there are an infinite number of atoms of space. But in actuality, there might be 10 to the 400 atoms of space. 10 to the 400 is very big, but it's not officially infinity. And so, but many things, if we're doing the mathematical physics of things, we want to take the limit number of atoms of space goes to infinity, because that's a more convenient mathematical kind of thing to do than to put a 10 to the 400 in there. Now, there may be effects where it matters that there are 10 to the 400 rather than an infinite number of atoms of space. We'd love to find those effects because those effects would be a way of kind of seeing to the discreteness of space. I mean, it's kind of like Brownian motion, which kind of clinched the idea of molecular structure of matter. We'd like to find the analog of Brownian motion for physical space, for example. Have some ideas about what that might be, but we don't we don't yet have a kind of this is the experiment to do to see that effect.
I see. So talking about innovation in science, we have been seeing the last few years a lot of hyping about AI and other kinds of stuff. But in your opinion, what was the biggest discovery of the last century, for example, that really made science to advance further? Was that AI? Was that other kind of innovations? What do you think?
Computation, I think, is the biggest thing that happened in the last century. I mean, the idea that you could have sort of rules that you could apply and that you can build up from. That's the big idea. And that's the idea that you're seeing kind of computation first as a practical tool, making kind of the computational X fields for all X. And second of all, as a paradigm for thinking about things with phenomena like computational irreducibility and so on. And I think that's the, if you look at the history of well, science, among other things, it's kind of defined by these levels of formalization that have been able to be done about the world. From the sort of very minimal formalization of human language, where you can use a word to describe lots of instances of a thing, to things like logic, to things like mathematics and so on. These are all ways of sort of formalizing the world to let you build up this bigger sort of tower of consequences. And that's what science has leveraged. And I think computation is a very big new kind of way of formalizing the world. And science has sort of begun to leverage that. I think it's interesting that a century ago, there were the big areas of physics that got developed, statistical mechanics. I mean, the second law of thermodynamics kind of started in the 1820s, but sort of developed more in the 1860s. And then, by 1900 or so, it was, well, everybody just assumed it was true, even though nobody had really given it. People had just thought there might be an argument to go from mechanics to statistical mechanics. And people sort of gave up actually finding that argument by about 1900. So, that was one thing, but that was sort of this idea of statistical mechanics, the idea of adding sort of a statistical probabilistic element to mechanics, big idea that led to second law of statistical mechanics and so on. Then, the other big ideas were relativity and quantum mechanics. And sort of interesting that those big ideas, well, those were big ideas in physics. In mathematics, the big idea was formalism, making things formal. Before the 1800s, if you said, what is mathematics? People would say, well, it's the study of, geometry of figures we can draw, and it's the study of kind of solving specific algebraic equations, things like this. What happened in the 1800s, starting in the 1830s and so on, with things like group theory and curved space and quaternions, things like this, was it's just like, we'll just write down axioms of mathematics and then just figure out their consequences. And that kind of flowered with people like Hilbert around 1900, just saying mathematics is writing down axioms and seeing their consequences. So this kind of notion of, was a sort of pre-computational idea that it's just like you write down a bunch of rules and then you see their consequences. And that was a thing that came into mathematics and physics. It was sort of a thing in statistical mechanics. And then kind of the formal ideas of relativity and quantum mechanics. So a bunch of advances in, and by the way, relativity and quantum mechanics also had this feature that they're very observer-focused theories. I mean, relativity is, you can't figure out simultaneity in an absolute way. You have to just do it based on sending light signals or something like this. Quantum mechanics, same kind of thing. You can't figure out the exact momentum and position. They're sort of observer-dependent theories. Well, those theories have been what we've been working with for the last 100 years. The thing that's been really exciting to me is that by thinking about things in a sort of fundamentally computational way, we have kind of a new direction. I mean, that's kind of why I called this book New Kind of Science, a new direction for thinking about lots of kinds of questions in science. I didn't realize when I wrote A New Kind of Science, I knew there were lots of kind of in a sense, near field applications of this computational way of thinking about things. What became clear in the last 5 or 6 years is that actually the applications of that idea are much deeper than I had imagined. So, for example, deep sort of notions about how you build physics, notions about how you build mathematics and what mathematics is. In the last year, ideas about what biology really is, and also what machine learning really is, and so on. And these are things which come from sort of, in a sense, almost philosophical thinking about computation, then a bunch of practical computer experiments. I think that people are very excited about AI right now. I think that's the bigger story is this computation story. AI is kind of an example of computation. It's an example of a place where what's happening inside a machine learning system. One of the big questions is, why does machine learning work? And that's been, we know there's this kind of, if you bash these neural nets hard enough, they'll learn almost anything we care about. And it's important to say anything we care about, because if you try and make them learn math, they're really bad at that. If you try and make them learn things that humans are good at, like recognizing pictures of cats from dogs, they do pretty well. And probably the reason for that is that neural nets are architecturally similar to brains. And so the things that brains do well, you can get neural nets to do well as well. And that's that's been sort of a surprise. We didn't know that was going to work, because we didn't really know what was important in brains, whether it was just this kind of things that are captured in neural nets, or whether it's some weird molecular quantum thing in brains. It seems that it isn't. It seems we can capture what's happening in brains in terms of sort of these simple idealized neural nets. But that allows one to do certain kinds of things. The question is sort of what's really going on inside. I think I've sort of understood this in recent times, that it's again a computational irreducibility story. The question is, how can you make a neural net that successfully does the things we want it to do? Well, you're kind of leveraging these lumps of computational irreducibility, and it seems that neural net training is basically finding lumps of computational irreducibility that will fit together in such a way as to do what you want. This is my analogy is you build a wall. You can either build it out of bricks, where you have a precise sort of engineering structure, you know how the bricks are going to be assembled, or you say, I'm going to pick up rocks off the ground and I'm going to try and fit them into the sort of places you need to build this wall. I think that second thing is what machine learning is doing. And it's the fact that there are all these weirdly shaped rocks that are the result of pieces of computational irreducibility that makes it possible to build up walls, in effect, that correspond to all these different kinds of things we want to do, like telling pictures of cats from dogs and so on. But I think sometimes people, when people say, I did it with AI, it's not always the case that they're doing it. If you think about AI as being this thing with neural nets, which is the most recent kind of instantiation of AI, that's not always the story. I mean, often the story is we enumerated a bunch of things computationally, and that's really back to the in a sense, traditional, although that tradition hasn't been going very long, of the traditional view of computation, so to speak.
I see. So it's usually said that in the past there are a lot of breakthroughs in physics, like the creation of statistical mechanics, thermodynamics, quantum mechanics, and it seems that nowadays breakthroughs are more rare. Do you think that's true? What do you think about that? Because there are a lot of scientists, famous scientists that did a lot of breakthroughs in the past, but it seems that there are not so many nowadays.
Well, a breakthrough, the typical progress of science is some new methodology is invented that often leads to a thing that's identified as a new field. And in that new field, with that new methodology, there will be some period of time, 5, 10, 20 years, where a lot of, quotes, breakthroughs get made because something new was opened up. And then a field becomes a well-known field, like physics, for example. And at that point, it's like, well, we know what physics is. It has certain methodology. We've picked all the low-hanging fruit with that methodology. And so what goes later is this long incremental process of figuring out more details. That process, when it comes to engineering and technology, is often in practice quite important, because you go from, we had one transistor to we have this, elaborate world of microprocessors and things over a period of 50 years or something. And that was a lot of engineering, and there's a qualitative difference in what you can do with a modern microprocessor and what you can do with one transistor. So that kind of incremental progress is more important typically in technology in areas like medicine and so on than it is in basic science, I think. I mean, basic science, you usually have this sort of incremental development, and then somehow some new methodology is invented, usually not from within the field. I mean, and usually when there's a new methodology, the field gets a new name. I mean, it isn't, whether it's biology to molecular biology, whether it's something like, well, whether it's mathematics to computer science.
Econophysics, maybe, sociophysics.
Yes, those are, I mean, well, that has a complicated history. I mean, people imagined around 1800 that, just as one had been able to do physics for gases, one will be able to do physics for society. And that hasn't quite played out yet. I think maybe it might soon, but that's been a long running, some things have been figured out, but I think there's more to be done there. But no, I think that this idea of sort of breakthroughs, people are always saying, oh, there are no breakthroughs, because they look at the existing fields. They say, oh, the prizes that are being given in this field, they're all for boring stuff. Well, that's because the field is a mature field where there's just incremental progress. And I think, the thing that's been interesting to me is sort of injecting this computational methodology at a foundational level into a bunch of fields. It's sort of breathing new life into these fields. And we get to have, we're having our period of low-hanging fruit picking. The fruit isn't quite as low-hanging as it might be. It's conceptually complicated. It is something that by the time you're dealing with computational irreducibility and so on, it's not something where we can immediately wrap our minds around these things. It's something where it's complicated to execute on it, but it's something where it sort of opens up these new directions. I mean, for me, it's been exciting to see that happen in physics, in foundations of mathematics, now in biology, and other areas. And it's kind of, I feel like there are ideas, like the original idea from 300 years ago of let's use math in science, which was, kind of the Newton, mathematical principles of natural philosophy. It's kind of, use math in science. That was an idea. And, there have been these other ideas, and we're now sort of operating on this new idea that has to do with, well, first computation, and then in more detail, these things about multi-computation and the importance of observers and these kinds of things, which feel to me like they're kind of unlocking a whole bunch of blocks that existed in science. I mean, I would say that sort of my earlier efforts that led to the New Kind of Science book, many areas were sort of blocked because they said there's complexity in this area. What do we do about complexity? How do we think about complexity? I think that the whole sort of notion of computational irreducibility, simple programs and so on, sort of unlocks that direction. And, it's kind of a dramatic thing that is not yet sort of clear in the history of science, is for 300 years, when people were trying to make models of things, they would use mathematical equations. That was kind of the standard for making models of things. Last 20 or 30 years, people make models using programs. And that's the more common form of modeling nowadays. And it's surprising that, I mean, that's a pretty big deal in terms of sort of the development of theoretical science. And I think we've got kind of another level of that, which is this whole thing about multi-computational observers and so on, which feels like it's sort of ready to open up a bunch of fields and to lead to what one can reasonably describe as breakthroughs, even though some of the questions that will be answered are questions that nobody even ever thought to ask before. And some of the questions that have been asked for a long time maybe will be answered, maybe not. Maybe it'll be different questions. I mean, if you said, we invent computer science, does that answer mathematics? The answer is no, but it answers certain kinds of things in mathematics, but it opens up a whole bunch of new questions.
I see. That's really interesting, because it seems to me that humans have this kind of desire for predictions. It's like it's inherent to us that we want to predict the phenomena we see around us. But computationally irreducible say that sometimes you cannot predict, you just need to do the math.
Yes.
So how do you see that in terms of this human spirit to want to have predictions?
Right. I mean, it is for us to exist in a coherent way, things have to be somewhat predictable. If nothing was predictable, we wouldn't have a coherent version of us. And I think it's sort of an essential feature of the way we perceive, the idea of consciousness and so on, is that we kind of, we develop this kind of thread of experience that is somehow consistent. And if it was just random stuff was happening all the time, we wouldn't have this kind of thread of experience that we associate with consciousness. And I think it's true. Humans differ from sort of all the rest of the natural world in this emphasis on kind of this single thread of experience. If we look at the sort of physical processes going on in our brains, there's a bunch of electrochemistry and all kinds of things, all kinds of electrical signals and so on. It's not that different from sort of things in solid state physics or something like that. What is different is that there's a big emphasis on the fact that we're sort of integrating all of these different inputs that are coming in and turning that into some sort of single thread of experience. And I think that's a special feature of us. And the fact that sort of we do that and we sort of want to have coherence, we tend to pay attention to things where we are going to be able to get that kind of coherence. Sometimes we have no choice but to deal with things that are computationally irreducible. But when we construct our world so that we have as much reducibility as possible. We could be, we make buildings where we don't have to deal with the question of whether it's going to rain tomorrow because we've got a roof over our heads. We kind of set things up so things are predictable as far as that's possible. And so so yes, I think and I think one of the things that I've been thinking about recently about economics, for example, is maybe the fundamental concept of value that we have in economics is associated with making things predictable, with having pockets of reducibility that we discover that allow us to sort of speed up ways to think about things in the world, predict what's going to happen in the world, and so on. And that's kind of it is a fundamental feature of the way that we sort of experience the world and want to experience the world and set the world up to be experienced by us.
I see. It's and where does free will fit in this picture?
So, I think when you say that something doesn't have free will, the typical sign that it doesn't have free will is you can say what it's going to do. You don't have to wait for it to do what it does. It is just, the moth is repeatedly bashing itself against the glass going towards a light. You say the moth doesn't have free will about that. It's just got some reflexive thing that it's doing, and we can predict what it's going to do. So the question of when you attribute free will to something, the typical thing that you're saying is, I can't tell what it's going to do. It seems like it has to be something inside it that leads to the behavior it has. And this is, again, a story of computational irreducibility. Even though we might know the deterministic laws by which our brains operate, and we might learn more about that over time, that doesn't mean that we can't say that we have sort of the experience of free will, because nothing can come outside us and say, I know what you're going to do. It's just we have to live it and do it to know what's going to happen. I mean, we can imagine at some time we'll be able to simulate brains. Maybe in digital electronics, we'll be able to simulate brains a bit faster than they happen. But still, the idea is sort of the same, that you have to actually go through all the steps to know what's going to happen. That's the sense in which one can say that even this brain that has an underlying deterministic set of rules is kind of exhibiting the phenomena of free will.
So computation is reducible is a kind of a free will because
Yes.
you have to live it so you know what's going to happen.
Yes.
And that's really beautiful because that goes to my next question because sometimes you probably I was asked this tons of times what is life, what is not life, but I have a different kind of question. What, in your opinion, is the purpose of life?
Well, okay. So I've been thinking a lot recently about what life is. Actually, people haven't asked me that so often. It's I used to think that life was something that when you looked at lots of processes going on in even abstract systems, that computational irreducibility was sort of the dividing line between sort of things that were inert and uninteresting and things that were sort of rich and interesting, and that life was just one point in this sort of space of computationally irreducible things. I've now recently come to the point of view that there's something differently special about life, just as I think there's something differently special about things like consciousness, and that has to do with this sort of, directing everything into this single thread of experience. But about life, I think the thing that seems to be special about life is that it was adapted to something. Not clear what it's adapted to. There can be all kinds of different fitness criteria, but there seems to be the case that if you think about all possible rules that you might apply, there are some rules that are adapted to something that is easy to describe, like the thing has as many offspring as possible, or some other simple to describe criterion. And I think that there's some sort of filtering of the set of all possible rules that one could use that correspond to the kinds of rules that seem to show up in life. It's kind of like in statistical mechanics, you are often calculating things on the basis of the fact that molecules can be in any possible configuration, any possible position, any possible momentum, and so on. And that alone, just saying it can be any possible of those things, gives you a bunch of results in statistical mechanics. So for life, I kind of have this guess that just knowing that there is some adaptation to something gives you potentially a kind of, I call it the rulal ensemble. That's my name for it right now. It may not, these names don't always survive to when I actually write these things up, but that's the current name that is sort of the description of an ensemble of possibilities that have been adapted to something. And I'm kind of suspecting that that's one of the things that's special about life. If you look at sort of a living system, you look at sort of what the molecules are doing. The molecules are doing these very complicated things. One might have thought, oh, it's just chemistry in life. They're just molecules that are sort of randomly bouncing around, just like in chemistry. And we can just think of life as being this collection of chemical reactions. I don't think that's correct now. What's become clear from molecular biology is that all these molecules have these very detailed mechanical dances that they do to make things happen, which we understand a few of. We don't understand most of them. It's this sort of bulk orchestration of what's going on at a molecular level that seems to be a characteristic feature of life. And it's kind of like, how do we understand, how do we model, how do we think about bulk orchestration? I think bulk orchestration is the essence of kind of what's happening in life, and we don't really have a theory of it yet. And maybe we will be able to get a theory. The biggest question for me right now is kind of, what's the question? So in other words, we make a theory of bulk orchestration. What do we expect are the sort of computationally reducible things that we can talk about given that theory? I don't know the answer to that yet. But that's kind of the sense in which there's kind of a something special that's achieved in life. By the way, it's achieved in technology as well. When we make a microprocessor, it's not just an electron gas in a semiconductor. Yeah. It's something with a lot more sort of, in a sense, purpose to it. And trying to understand, is there a theory of microprocessors that's beyond saying it's an electron gas, which is a very bad theory? I don't know the answer to that yet.
I see. Talking about about the company, what should we expect for the next decades for Wolfram Mathematica?
Well, I mean, I started Wolfram Research in 1986. So we've had, almost 40 years of building things. And what have we been building? What we've been building is a computational language to sort of talk about the world computationally. I mean, I kind of see our mission as being a much modernized version of the mission that people had 500 years ago in inventing mathematical notation. It's kind of like you could talk about math in words and kind of wave your hands about it, but then there started to be a systematic notation with plus signs and equal signs and so on. And that's what launched, made possible algebra and calculus, eventually the mathematical sciences. Kind of our goal is to kind of represent computationally things in the world and to have a language where you can think to yourself in that language, but also, unlike with mathematics, where the language is what it is, and you can think in terms of that mathematical language, the big kicker with computational language and with Wolfram language is the computer can work stuff out for you. And this is a huge kind of, huge sort of power assist to your thinking. And there's, we've seen the sort of slow development of these fields of computational X. Um, the there's sort of been, during that period of time, there's been a vast increase of sort of software engineering and kind of do things with computers. People are realizing now that some of the things that, oh, you write all this code in some low-level language, that's a programming language that's sort of telling the computer what to do. A lot of that is kind of boilerplate, and an AI can just trot it out for you too. And sort of people are realizing that there's parts of doing things with computers that actually involve computational thinking, and there's parts of doing things with computers that, in a sense, are just sort of computational manual labor, where you're just, writing a bunch of code to implement some checkout mechanism for some website or some such other thing. And that, what we've been trying to do in all these years is to sort of take this whole domain of computation and find the sort of primitive lumps of computational work that are worth sort of implementing and being able to let people reuse. So we've kind of dramatically automated a lot of this kind of computational process. And what we see is that people across sort of the leading edge of a huge number of fields have sort of cottoned on to this idea and are able to use this kind of this sort of power assist to their thinking to be able to do all kinds of important things, which has been really satisfying over the last 35 years or so to see that happening. When it comes to kind of the lower level, let's do computational manual labor, somewhat frustratingly, people often haven't cottoned on to this idea. It's like, we're supposed to write this piece of code. We've got a specification. It's going to take us a month to write this piece of code. If you wrote it in Wolfram language, it would take an hour. But the problem is that the person who is doing that month of work is thinking, I've got a month of work to do, and thinking about what is the next thing to specify is not their job. And so people who tend to use our tech a lot are the people who are CTOs, CEOs of tech companies and so on, who are, they imagine things they want to do, and then, well, we've got a very automated way to get those things done. And so it's like, okay, we can get it done in a few hours and see what we get from that. And then they go on to the next thing that they're figuring out. So kind of what we're really trying to do is to provide this tool for computational thinking, this language in which to think computationally, and then the actual machinery to get that computational thinking actuated in the world, so to speak. And that's been a long-term mission, and seeing sort of how we kind of implement that in different computational X areas, see how we can give sort of neural net AIs this kind of computational tool, because what we're doing is something rather different from what the AI does well, is this kind of broad but shallow kind of thinking, in a sense, as opposed to this kind of deep formal thinking that's made possible by computational language. And so sort of the best thing is you use something like our notebook assistant, which uses LLMs inside, and you kind of tell it vaguely what you want, and it will find the closest island of computation, so to speak, to the thing you asked about, show you a particular example of how to do it, and then you're sort of off and running, thinking computationally and more sort of in a more formal way about what you're trying to do. So in terms of what we're doing, well, this project of sort of making the world computational is a never-ending project.
Yeah.
And I've been at it for 45 years so far, and expect to keep doing that. And there's more and more that can be made computational. And as we build up the sort of taller tower of sort of computational ability, we see even further what can be done computationally. So that's a direction. I think that there are lots of specific technologies that sort of integrate modern neural net AI. There are things that I think it may be the case that neural net AI is kind of a sort of a fuzzy way to do things, and some of what it gets done that way we now know is possible, but there's a much more direct industrial formal way to do those things. And so some of the things we may be doing involve sort of taking the things that neural nets have been a wow that they do, and finding sort of more systematic ways to do the same kinds of things. I mean, in a sense, neural nets, like humans, don't get to run code in their brains.
Yeah.
We're providing the code that can be run, and we're making that interface to neural net AI is an important thing. I mean, there are if we look at the roadmap of things that we're doing, well, I had a roadmap back in 1991. We recently finished that one.
Really?
So there's always these projects that we do, and a lot of projects we do have 10-year type timeframes. So some things we know what's going to happen in that period of time. I would say about half the things that we end up delivering are things that have been gestating for very long periods of time, and half are things that are made possible by other technologies that emerge in the world or other kind of interests that people develop that we can make use of.
I see. Well, Stephen, thank you very much for your time and for your kindly agreeing with this interview. Since our audience is mainly Brazilian, I would kindly ask you, you've been to Brazil, right?
Once.
Once, yeah. So I would kindly ask you if you have like a message for Brazilian people. I come from the solid state physics lab from Rio Claro, it's close to São Paulo City. And do you have a message for us, for Brazilians, like scientists?
It's funny because one sees science being done and technology being done all around the world, and every country has a certain personality in the way that it does things. Brazil seems like a very intellectually entrepreneurial kind of place. Not true of all places. I mean, there are places where it's like, we'll do the things that have been done before type thing.
Okay.
And I think that's an opportunity, so to speak. And I think some of these kind of it's been nice for me to see that a bunch of people from Brazil have been interested in some of these sort of new developments in science, in sort of rheology, and some of these things that are now sort of getting opened up. That's, one of the things to realize about kind of the world of science today is when there is a new area, when there's a new methodology, when there's a new thing that opens up, it's kind of a level playing field. I mean, when there are things where you've got to have built up expertise, facilities, and so on in a particular area, then kind of the country that has had sort of the most development, the longest time to develop those things is going to win. But when things are fresh and new, and the playing field is much more level, and that's, I think, sort of an opportunity for Brazil and Brazilian scientists and so on. There are new things to do. Brazil is a place where people seem to think about new things. I think there's an opportunity, and it'll be cool to see that come to fruition.
Well, thank you very much. It was quite an honor to be here with you, and thank you very much for your time and for this opportunity.
Thanks.